Good evening. Welcome to the QCIS channel. We're on this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones. I got another good one for you right here on the STEM channel. And tonight, I'm going to get more into some of the fundamentals of engineering type of subjects. And these are actually basic engineering subjects that you learn in college. And if you don't know these subjects, it's going to be hard for you to advance into the more complex subjects. So tonight, I'm going to talk about basic electronic or electric circuits. Now, you know there's Kirchhoff's law, which states that V equals I times R, which V is voltage, R is resistance, and I is current. And you can manipulate that formula to find all three variables. Now, when it comes to circuits, you're going to see parallel and, of course, series circuits, just like you see in the background. That's a circuit. Circuit always starts with, could be a battery, some type of voltage. Then you have your resistors with the colors on them. And those resistors could be placed in a series or they could be parallel. So when I talk about basic circuits, these are very basic. There are three types of circuits. Now, I've already given you the first two. Now, the third one is just a combination of the first two. So basically, there are three types of electrical circuits: series, parallel, and a combination, or I call them series parallel circuits. Now, again, as I stated for you a minute ago, each type has a distinct way the components are connected. And that affects how the voltage behaves within the circuit. Again, basic circuits. There are three types of circuits: series, parallel, and the third one is a combination that's series and parallel. Now, of course, the way each circuit is connected, it affects how the voltage will behave within the circuit. Now, in simplest form, an electrical circuit consists of three fundamental parts: a power source to drive the electrical current around the circuit, which is a battery; a conductor to carry the current around the circuit, which is a wire or some cable; and a load that has a resistance. Could be a heating element or a light bulb. But that's what a basic circuit is. Now, of course, I'm not going to get into alternating current and direct current, but I will talk about that in the future, because that is part of circuitry as well. Inductance. So I'm going to go ahead, present this PowerPoint to you. And I actually took a basic circuits class. Basic circuits class. I took a basics and I enjoyed it. I love circuits. Electricity is fun. You see it everywhere you go. You have it in your house, you have it in your car. So basically, what I'm going to talk about are the laws when it comes to circuit concepts. Like when we get into this lesson, in order to understand the definition, You have to understand the laws as well. So when we have basic circuit concepts, just like in every science, there are a system or there is a system of units. Now, the units could be in English units or SI units. Now, when I took courses in college, we had some English units, but a lot of the units were in SI units. And I'm talking about meters, kilograms, seconds, amperes, degrees of Kelvin, candela as the fundamental units. Now, also, when it comes to circuits, we use prefixes. The prefixes are in scientific notation. They go from smallest to largest. Now we have pica, which is 10 to the negative 12. Then we have a nano, it's 10 to the negative ninth. Micro is 10 to the negative 6. Milli, which is 10 to the negative 3. Now, what is 10 to the 0? 10 to the 0 is always going to be 1. In fact, any number to the 0 power is 1. So when we get into your higher values, we have your kilo. That's your prefix, kilo, which means 1,000. 10 to the third. Mega is 10 to the sixth. Giga is 10 to the ninth. Tera is 10 to the 12th, which is trillions. Now, when we come down to concepts, well, what is electricity? Well, one might define electricity as the separation of positive and negative charges. When the charges are separated and stationary, we call this static electricity. Now, where have you heard that word static from? Because when anything is static, everything equals zero. That's right, mechanics and statics. Well, the charging of a capacitor is an example. The separation of a charge between clouds and the earth before a lighting discharge is known as static electricity. Again, when the charges are separated and stationary, we call this static electricity. So basically, the charging of a capacitor is an example. Now, the separation of charge between clouds and the earth before a lightning discharge is a static electricity. And also when the charges are in motion, changing with time relative to one another, we have what we call variable electricity. Now, some of the basic concepts. The unit of current is always an ampere. And we note that 1 ampere, remember, I gave you a lesson on conversions. Well, with basic electric concepts, we're going to have conversions. 1 ampere equals 1 coulomb per second. We normally refer to the current as being either direct or alternating. What I mentioned before, AC or DC. You see, direct is basically a straight line. And if you have alternating, you know why there are waves when it comes to alternating current? Alternating current goes in cycles. It goes pi over 4, 3 pi over 4, 2 pi. In other words, there you have, it's more or less, if you have an oscilloscope, you see that sine wave. Alternating current is sinusoidal. Means you have a sine wave going up and down, and all of the phases and cycles, goes in cycles. They're equal. Again, you start off at 0, then you go up to pi over 4, pi, 3 pi over 4, 2 pi. Also, in solving for current in a circuit, we must assume a direction. Solve for the current and then reconcile the answer. This is what happens in the illustrations below. So in the diagram above, I have current I is actually 4A as assumed. The actual positive direction of I2 is equal to negative 3A. And in the opposite direction of the arrow for I2. See it in both of these diagrams. And when it comes to science, you must understand diagrams. But again, I'm just giving you the basics right here. So when we have quantities, the basic quantity for electricity is always voltage. Voltage is also called an electromotive force, known as EMF. It is also called potential, coming from the expression potential energy. Now, if you're not familiar with potential energy, that is energy in motion, where potential or kinetic energy, no, actually kinetic energy, when something is kinetic, it's energy in motion. When something is potential, it's actually energy stored, and there are equations for potential and kinetic energy. Now, you have to understand that voltage is not an energy. So let me break down a scenario for you. Suppose 1 coulomb of charge is located at point B and 1 joule of energy is required to move the charge to point A. And we say that AB equals 1 volt, which equals 1 joule per coulomb, which equals 1 Newton meter per coulomb. Well, if VAB equals 1 volt, and it states that the potential of a point at voltage point A is 1 positive with respect to B, then the sign associated with that voltage is also called its polarity. So let's get into some basics right here. As in the case for current, we must assume a positive direction, which is polarity, with a voltage. So consider the 3 diagrams. So each of the above diagrams gives you all the same information. Now, keep in mind that when we assume a polarity for voltage, you must understand that when we solve the current for the voltage, we may find that the actual polarity is not the polarity that we assume. So the negative sign for 6 volts indicates that if the red lead of a voltmeter is placed on the positive terminal and the black lead on the negative terminal is placed, then the meter will read downscale or negative 6 volts. A digital meter would read negative 6 volts. So what would an analog meter do? Now, again, we're using a lot of digital. We're not using analog as much as we used to. So, in summary, we should remember that P equals delta W over delta Q. This can be expressed in differential form as B equals dW dQ. You can always find a derivative if you're utilizing calculus, but I'm not going to go into calculus, but I'm going to show you how all these equations work, because now I'm going to talk about power. And power, if something is defined as a change of any type of rate change, then we deal with derivatives. So power is defined as the time rate of change for doing work. So we express this as P equals dW dt. So we can write the equation as follows. P equals dW dQ times dQ dt, which equals VI. Now, one thing that you must understand is when we talk about power, power is expressed in watts and kilowatts. on your bill, and that will tell you how much power you used. And there's a charge behind that. A lot of individuals don't understand power because they don't know the units for power. Power is in watts and kilowatts. Now, in any closed electrical circuit, power is both supplied and absorbed. So the amount of power that is supplied must be equal to the amount that is absorbed. Stated another way, we can say that the law of conservation of energy must hold. Therefore, in any electrical circuit, the algebraic sum of the power must be zero. Now, sounds familiar. It's like statics. No statics, if I apply 200 pounds of force going down, in order for the force to equal zero, I have to apply 200 pounds of force going up. Well, it's the same thing with an electrical circuit. So if I supply 10 watts of power, in order to get zero, I have to absorb 10 watts of power. Now, power and energy. I just mentioned it. When we pay our electrical bills, we pay for watt hours, but because this is such a large number, we usually think kilowatt hours. Now, a kilowatt is 1,000 watts. So basically, a cost of 1 kilowatt hour is approximately 4 to 8 cents. Now, a profile of the power you use during a day may be shown below. Now, again, the energy we pay for is the area under the power time curve. And this is the power time curve. Now, anytime you have an area under something, we go to calculus. Like we go to W equals T0 T2 PDT, which equals T0 TVI dt. We're taking the integral of power. So you have limits of integration. That's how you get that formula. We also adopt the passive sign convention in order to define the sign of supplied power and the sign of absorbed power. So you consider the following. Power supply. If the assumed direction of the current leaves the assumed positive polarity of the voltage, then what happens? Power is supplied. Now, if the assumed direction of the power enters the assumed positive polarity of the voltage, then power is absorbed. In other words, they cancel each other out. Also, we deal with charge. Charge is the most fundamental quantity of electrical circuits. In most electrical circuits, the basic charge is that of an electron, which is it's negative 1.602 times 10 to the 19th coulombs. And there's a formula for that. Now, the entity charge is expressed as Q, and that's uppercase Q or lowercase q. If the charge is constant, then we use uppercase Q. If the charge is in motion, we use either QT, which is a lowercase q, or we use lowercase q, lowercase t. Now, according to fundamental laws, charge cannot be either created or destroyed. It can only be transferred from one point to another. So we define charge in moment as current. That is, IT equals dq dt. And again, you look at the examples, and you can see the examples by the sign convention. Up here you have all the power that's supplied and the power that's absorbed. And if you look at it, 4 times 5 equals 20, all across the board here in that circuit. You have power supplied, but in these four diagrams, it's all power absorbed. Now, when we deal with electricity, we also have circuit elements. So basically, we classify circuit elements as either active or passive. So a passive element cannot guarantee or cannot generate energy. Again, passive elements cannot generate energy. Common examples of passive elements, again, common examples of passive elements are resistors, capacitors, and inductors. We will see later how capacitors and inductors can store energy but cannot generate energy. Active elements can generate energy. Common examples of active elements are power supplies, such as batteries and operational amplifiers. Of course, your oscilloscope as well. So for the present time, we will be concerned only with sources. These types of sources we will consider are independent and dependent. Now, ideal independent voltage source is characterized as having a constant voltage across its terminals, regardless of the load connected to the terminals. So the ideal voltage can supply any amount of current. Furthermore, an ideal independent voltage source can supply any amount of power. The standard symbols of the ideal independent voltage source are shown below. And in physics, take circuits, you're going to use a lot of these symbols. This one you use most often. Now, an ideal independent current source is characterized as providing a constant value of current regardless of the load. So if the current source is truly ideal, it can provide any value of voltage in any amount of power. So the standard symbol used for the ideal independent current source is shown below. Now, the ideal independent voltage and current sources are models. As such, they are subjected to limitations. For example, an independent voltage source that one commonly works with cannot pull out 1 times 10 to the 320th power volts. Neither can an ordinary independent current source put out 4 times 10 to the 765 amps. So we must always keep these limitations in mind. Otherwise, one might think that one can start an automobile engine with a 12-volt radio battery. Now, when it comes to dependent voltage sources, well, basically they're characterized by depending on a voltage or current somewhere else in the circuit. So the symbol for the current source is shown below. Note it's a diamond shape. Now, a circuit containing a dependent voltage is also shown. So this is what we call a circuit with a controlled dependent voltage source. Now, if you look at this circuit right here, you have your power source, which is your voltage, and of course, you have your current. Now, if you look at this circuit right here, I can tell you what it is right now. This is a combination because you have your resistors right here, which are in ohms. They're in series, which you also have parallel circuits. So this is a combination circuit that I was talking about. And there's a mathematical formula that you can figure out to find out what kind of voltage, power, and even what kind of current you have traveling through this circuit. But if you want to see a combination circuit, this is it right here. Again, both of these resistors The unit is ohms. These are what you call series circuits. These resistors are in series, while these resistors are in parallel. Now, a dependent circuit source is characterized by depending on a voltage or current somewhere else in the circuit. The symbol for a dependent current source is as follows, and it's shown. And again, a circuit containing a dependent source, it is shown below. So if you look at it again, you have your power source, you have your series, and your parallel. So a circuit with a voltage controlled dependent current source. That's what this is as well. Charge examples. Well, these are your equations for charge. And I'm going to, when I get a whiteboard, I'm actually going to go and show you how I come up with all these answers. And this is especially important if you're going for your fundamentals of engineering exam, and you could be taking electrical circuits in college as well. Now, find the current in an element if the charge flowing through the element is QT, and that equals 3T cubed plus 6T squared plus 8T minus 4. Now, when you get something like a dQ dt, that's telling you it's a derivative. So when you take a derivative of something, what you're going to do, you're going to take the coefficient and multiply it by the exponent. So here's how it's done. I have 3t cubed. Now, what happens when you multiply the coefficient times the exponent? The exponent is reduced. And this is if you do first derivatives, second derivatives, and third derivatives. Now, I'm going to do a first derivative for you right now. So you have 3t cubed. So what I'm going to do is, to get the first derivative, I'm going to multiply the coefficient times the exponent, and I'm going to come up with 9t squared. So what I did was, to show you, I took the coefficient, multiplied it by the exponent, and reduced the exponent once I got my product. And I'm going to do the same thing for the second part of this equation. 6t squared. So 6t squared, well, to get derivative, it's going to be 12t. And then 8t is simply going to be 8. And that's your, and that is your charge right there. 9t squared plus 12t plus 8. I took the derivative. Now, if the current in an electrical device is given by IT equals 2t plus 4, with Q0 equaling 1.5 coulombs. That is not Celsius, that's coulombs. So find the charge flowing through the device from this equation. So let's plug everything in. So the equation is IT dt. Now you have your limits of integration here. They go from 0 to t. So what you have to do is you have to look at all of the information that is given. So your equation is qt equals 0 to t, which are your limits of integration, times it dt plus q to the 0. So we already have everything given, so you set everything up. So you plug in for it 2t plus 4 that we were given, and for q0 we plug in 1.5. So now that we have that situated, remember, when you take an integral, you're actually taking the opposite of a derivative. Remember that. So when we actually go and put everything together, and you can always check to see if you have the right integral by actually taking the derivative. That's a trick that even my professors never told me. So when we go ahead and integrate 2t plus 4 dt plus 1.5, well, we end up with t squared plus 4t plus 1.5. That's how we integrate everything. That's calculus. And then, given the equations below, of course, calculate the power supplied by each device. Show the sum P equals 0. Verify P sub equals P absolute. P sub is power supplied, which equals power absolute, which equals 104 watts. I didn't go through the calculation, but I could if I had the right tools. But here are some examples. Power supplied, 24. So you take 24 times 4, you get 96 watts. Power supplied, 8 volts. Minus 4 times 8 equals minus 32 watts. And you can do the same thing for all the rest of these equations. And there you have it. What I've given you, that's the fundamentals of electrical concepts. Now, remember something. Kirchhoff's law. I will V equals I times R, or I equals V over R. Coulombs, amperes, ohms. That's how you look at electricity. Now you remember, direct current, it's just a straight line. So my direct current is at 2, it's going to be 2 across. But when we start dealing with cycles, I said phases, but it's really cycles. Well, alternating current, you know why they call it alternating current? Because the cycles alternate, because you have a peak that's positive and you have a valley which is negative, and then it goes back up to positive. It alternates, negative. In other words, they cancel each other out, and that's known as sinusoidal. 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 In other words, you start at 0 and you're going to go to pi. You're going to go to pi over 2, 3 pi over 2, 2 pi, and then you're going to come right back down and negative. And if you know what an oscilloscope looks like, when you're testing the circuit, you're going to see that sine wave. And remember something. When you have your electric bill, we're not charged in watts, we're charged in kilowatt hours. Always look at your bill. Basically, when it comes to power, in order for you to get 0, the power supplied must equal the power absorbed, just like in statics. And that is the basics for electricity. There are a lot of equations that you need to know to figure out some of these circuits. You can even go into the lab and play with some of these circuits. And I always believe the best way to look at these equations is to actually go test everything in the lab, get the data, and utilize the calculations. Now, if you have a calculator like this one on the FE examination, because you are actually going to see some circuits on there. You'll see parallel, you'll see series, you'll see a combination of parallel and series. And I just gave you an illustration on what a combination circuit looked like in tonight's presentation. But thank you for viewing this content right here on the basic electrical circuits concepts. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some social, some political content, you check out my main channel, the 411 Talk Zone Radio Show channel. Now, here's where you can find me. For the 411 Talk Zone Radio Show channel, you can find me right here on YouTube. You can also find me on X, formerly Twitter. You can find me on True Social and Rumble. And for the QCIS channel, you can find me right here on YouTube, X, formerly Twitter, and LinkedIn. And a little thing about LinkedIn, I've been getting a rash of people who want me to connect. All right. I put information up on LinkedIn for people who are only interested in science, technology, engineering, and math. That's it. If they want to learn something, I'm not interested in getting with your firm or hearing from you. If you are in finance, this is a STEM channel, and that's what I use LinkedIn for, because there's a lot of good information up there. So if you are in the STEM programs and you're interested in STEM, the videos that I record are also posted right up there on my LinkedIn page. But I just want individuals to know that if you're not doing STEM, don't waste your time to connect with me, because I will not answer. And my goal is to teach individuals who are preparing for the FE and PE examinations and who are taking certain subjects in school to get by through engineering programs. Because in order for you to get through an engineering or an engineering technology program, or even a physics class, you have to understand the basics. And again, when I get the whiteboard working where I can actually do problems and show you units, oh, you're going to enjoy it. And I'm going to continue to build this channel up, because this is an educational channel and I want individuals to learn. Because let me tell you something, STEM is fun. Even when you're in school, yes, some of your professors might give you some of the hardest homework, but I can tell you, like tonight, did some problems myself, and going to get into some statics, going to get into some dynamics, some thermodynamics, some material science, and please leave a comment. Let me know what you think. Well, once again, just want to thank you for viewing this content right here, QCIS channel. On this channel, get a daily dose of science, technology, engineering, and math. Till next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.